spoke of the music of the spheres, a cosmic harmony that connected all celestial bodies in an invisible symphony. What they intuited thousands of years ago, we now know to be remarkably close to the truth. You see, when we think about sound, we usually think about vibrations travelling through air. When you pluck a guitar string, it vibrates and pushes air molecules back and forth, creating waves that travel to your ears. But the universe operates on a much grander scale, with forces and phenomena that create vibrations and waves in ways that would make our earthly sounds seem like tiny whispers in comparison. Stars, these massive spheres of plasma and nuclear fire, are not the static, unchanging lights they appear to be from our earthly perspective. They are dynamic, living entities that pulse, vibrate, and oscillate in complex patterns. Think of a star as a gigantic musical instrument, perhaps the largest drum in the cosmos, with its surface and interior layers creating standing waves and vibrations that ripple through its entire structure. These stellar oscillations, as astronomers call them, happen because of the incredible forces at play within a star. The outward pressure from nuclear fusion in the core battles against the inward pull of gravity, creating a delicate balance that isn't perfectly steady. Instead, it's like a cosmic dance, with the star's material moving in and out, creating waves that travel through the stellar medium at specific frequencies. Imagine dropping a pebble into a still pond and watching the ripples spread outward in perfect circles. Now imagine that pond is made of plasma heated to millions of degrees, and instead of one pebble, there are countless sources of disturbance creating overlapping waves of incredible complexity. This is what's happening inside every star, including our own sun, every single moment of every day. The beautiful thing about these stellar oscillations is that they create acoustic waves that travel through the star's body. These waves bounce off different layers, reflect from the surface, and create standing wave patterns that are as unique as fingerprints. Each star has its own acoustic signature, its own way of vibrating, its own song. But here's where it gets even more fascinating. When a star is healthy and in the prime of its life, these oscillations follow predictable patterns. The star hums along in its cosmic rhythm, maintaining a relatively stable beat. But as a star ages, as it begins to exhaust its nuclear fuel and approach the end of its life, these patterns begin to change. The music becomes more complex, more urgent, more dramatic. It's like listening to a musician who starts playing a familiar tune but gradually introduces variations, improvisations, and crescendos that build toward a final climactic moment. The star's song becomes its swan song, a performance that tells the story of its impending transformation. Now, you might be wondering how we can possibly hear these stellar songs when space is a vacuum and sound can't travel through emptiness. This is where our story takes an even more remarkable turn, because the universe has given us a way to listen that's far more elegant and profound than anything we could have imagined. Enter gravitational waves, one of the most beautiful and mysterious phenomena in all of physics. Albert Einstein predicted their existence over a century ago, but it wasn't until 2015 that we finally developed the technology sensitive enough to detect them. And when we did, it was like suddenly gaining the ability to hear music that had been playing around us our entire lives. Gravitational waves are ripples in the very fabric of space-time itself. When massive objects accelerate, particularly when they are involved in cosmic events of tremendous energy, they create disturbances that propagate outward at the speed of light. These waves are so subtle that they stretch and compress space by amounts smaller than a proton, yet they carry with them the signatures of the most violent and dramatic events in the universe. Think of space-time as a vast invisible ocean, and massive cosmic events as stones being dropped into this ocean. The ripples that spread outward carry information about the stone that created them. The size of the stone, the speed at which it hit the water, the depth at which it sank, all of this information is encoded in the wave patterns. When two black holes spiral into each other in a cosmic dance that takes millions of years to complete, the final moments of their merger create gravitational waves that sweep across the universe. When a neutron star, the incredibly dense remnant of a massive star, suddenly collapses or collides with another neutron star, it sends out gravitational waves that carry the story of that cataclysmic event. And here's the truly magical part. When scientists detected these gravitational waves for the first time, they didn't just see data on a computer screen. They converted the wave patterns into sound frequencies that human ears could hear. The result was literally the sound of the universe itself, the audio signature of cosmic events so powerful that they shake the very foundations of reality. The first gravitational wave ever detected, which scientists call GW150914, created a sound that has been described as a chirp. It started as a low-frequency hum and quickly rose in pitch and intensity before suddenly cutting off. This chirp lasted only about 0.2 of a second, but it represented the final moments of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging into a single larger black hole. In those 0.2 of a second, the universe sang to us. It told us the story of two massive objects that had been dancing around each other for eons, gradually drawing closer and closer until they finally embraced in a cosmic collision that converted the mass of 3 suns into pure gravitational wave energy in a fraction of a second. But gravitational waves from black hole mergers are just one type of cosmic sound. Stars themselves, particularly in their final moments, create gravitational waves that tell stories of stellar death and transformation. When a massive star explodes in a supernova, when a neutron star suddenly changes its spin, when stellar remnants collide and merge, all of these events create ripples in space-time that carry acoustic signatures we can detect and listen to. To truly understand the sound a star makes before it dies, we need to understand the different ways that stars can die, because each path to stellar death creates its own unique acoustic signature. Just as different musical instruments create different timbres and tones, different types of stellar deaths produce different gravitational wave patterns and frequencies. Most stars, including our own Sun, will end their lives relatively quietly. These smaller stars will gradually exhaust their nuclear fuel, expand into red giants, and then gently shed their outer layers to become white dwarf stars. This process takes millions of years and doesn't create the dramatic gravitational waves that we can detect from Earth. But even these gentle deaths have their own subtle music. As a star like our Sun approaches the end of its life, its internal oscillations begin to change. The star's core contracts and heats up, while its outer layers expand and cool. This creates new patterns of convection and oscillation that change the star's acoustic signature. The star's song becomes deeper, more complex, with harmonics and overtones that weren't present in its younger days. Imagine a musician who's been playing the same melody for billions of years, but now begins to add variations, embellishments, and emotional depth to the performance. The fundamental tune is still recognizable, but it's richer, more nuanced, touched with the wisdom and experience of age. But the most dramatic stellar death songs come from the massive stars, those giants that are at least 8 times the mass of our Sun. These stars live fast and die young, burning through their nuclear fuel in just a few million years rather than the billions of years that smaller stars enjoy. And when they die, they don't go quietly. The death of a massive star is one of the most violent events in the universe. As the star exhausts its nuclear fuel, it can no longer maintain the outward pressure needed to balance gravity's inward pull. The core collapses in a matter of seconds, reaching temperatures and densities that rival those found in the early moments after the Big Bang. This collapse happens so quickly that it creates a shock wave that races outward through the star's layers. When this shock wave reaches the surface, it blows the star apart in a supernova explosion that can outshine an entire galaxy for weeks or even months. The energy released in this explosion is almost incomprehensible, equivalent to the Sun's entire energy output over its entire 10 billion year lifetime, all released in a matter of seconds. But before the visible explosion, before the light reaches us, the collapsing core creates gravitational waves that race outward at the speed of light. These waves carry the acoustic signature of the core collapse, a sound that tells the story of matter being compressed to unimaginable densities in a fraction of a second. The gravitational waves from a core-collapse supernova create a sound that's been described as a whoop, a sudden, sharp increase in frequency that peaks and then gradually declines. It's like the universe taking a sharp, surprise breath as it witnesses the transformation of the massive star into a neutron star or black hole. Scientists have used computer simulations to model these core collapse events and convert the resulting gravitational wave patterns into audible sounds. The results are haunting and beautiful, like the voice of the universe itself expressing both the violence and the wonder of stellar death. After a massive star explodes in a supernova, what remains is often a neutron star, one of the most extreme objects in the universe. These stellar remnants are only about 12 miles across, but they contain more mass than our entire sun. To put this in perspective, a teaspoon of neutron star material would weigh about 6 billion tons on Earth. Neutron stars are like cosmic lighthouses, spinning rapidly and emitting beams of radiation that sweep across space. When these beams happen to point toward Earth, we detect them as pulses of radio waves, which is why we call these objects pulsars. The pulses are incredibly regular, like the ticking of a cosmic clock, with some pulsars keeping time more accurately than the best atomic clocks on Earth. But neutron stars don't just emit radio waves, they also create gravitational waves, and these waves produce some of the most subtle and beautiful sounds in the universe. Unlike the dramatic chirps of black hole mergers or the sharp whoops of supernovas, neutron stars create continuous, gentle gravitational waves that sound like whispers or sighs. These continuous gravitational waves happen because neutron stars aren't perfectly smooth spheres. They have tiny mountains and valleys on their surfaces, imperfections that are only fractions of an inch high, but that create gravitational wave signals as the neutron star spins. It's like having a cosmic record player with a slightly warped record, creating a continuous gentle hum that carries across the universe. The sound of a neutron star's gravitational waves is incredibly subtle, like a distant flute playing a single pure note that never wavers or changes. These waves are so weak that we haven't yet detected them directly, but we know they must exist based on our understanding of neutron star physics. The fact that we can predict their existence, calculate their frequencies, and even imagine their sound shows how far our understanding of the universe has come. Some neutron stars are part of binary systems, orbiting around other stars or even other neutron stars. These systems create more complex gravitational wave patterns as the two objects spiral closer together over millions of years. The waves start as barely detectable whispers, but gradually grow stronger and higher in frequency as the orbital decay accelerates. When two neutron stars finally merge, the result is a killer wave, a gravitational wave event that's been described as one of the most beautiful sounds in the universe. The merger creates a complex pattern of waves that sound like a cosmic song, with harmonics and overtones that tell the story of two incredibly dense objects becoming one. The first neutron star merger detected by gravitational wave observatories was called GW170817, and it created a sound that lasted for about 100 seconds. Unlike the brief chirp of a black hole merger, this was an extended performance, a cosmic aria that began with subtle oscillations and built to a crescendo that could be heard across the universe. But neutron star mergers don't just create gravitational waves, they also produce visible light, gamma rays, and other forms of electromagnetic radiation. This means that GW170817 was the first cosmic event that we both heard and saw, marking the beginning of what scientists call multi-messenger astronomy. Perhaps the most mysterious and fascinating stellar death song comes from the formation of black holes. When the most massive stars die, when their cores are so heavy that even neutron star matter cannot support them against gravity's relentless pull, something extraordinary happens. The core collapses beyond the point of no return, creating a region of space-time where gravity becomes so strong that nothing, not even light, can escape. The moment a black hole forms is like the universe holding its breath. In the fraction of a second during which the stellar core crosses the event horizon, the boundary beyond which nothing can return, the dying star creates a gravitational wave signature that's unlike anything else in the cosmos. But black holes, once formed, don't remain silent. They continue to sing, particularly when they encounter other black holes in the vast darkness of space. Over billions of years, two black holes can find each other and begin a cosmic dance that eventually leads to merger, creating some of the most powerful and beautiful sounds the universe has ever produced. The dance of two black holes is a story that unfolds over cosmic time. At first, when they're far apart, they barely affect each other. But as they radiate away energy in the form of gravitational waves, they slowly spiral inward. The process is so gradual that it can take longer than the age of the universe for two black holes to complete their final merger. But as they get closer, the dance accelerates. The gravitational waves become stronger, higher in frequency, and more complex. What starts as a barely detectable whisper becomes a song, then a symphony, and finally a cosmic shout that can be heard across billions of light years. The final seconds of a black hole merger create a gravitational wave pattern that scientists have described as one of the most beautiful sounds in physics. It's a chirp that starts low and rises in pitch and intensity, like a cosmic bird song that builds to an impossible crescendo before suddenly cutting off. In those final moments, the two black holes are orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. The gravitational waves they create are so powerful that they carry away energy equivalent to the mass of several suns, all converted into pure gravitational radiation in a matter of seconds. The sound of a black hole merger is both violent and beautiful, representing the ultimate expression of gravity's power and the universe's ability to create music from the most extreme physical processes imaginable. It's a sound that speaks to the fundamental nature of space-time itself, a reminder that the universe is not just a collection of objects moving through empty space, but a dynamic, living entity capable of creating its own music. When scientists first heard the gravitational waves from black hole mergers, many described the experience as deeply moving, even spiritual. It was the universe itself, singing to us across billions of years and billions of light years, sharing the story of cosmic events so powerful that they shake the very fabric of reality. These black hole songs are now being detected regularly by gravitational wave observatories around the world. Each merger tells a unique story, with different masses, different spins, and different orbital characteristics, creating different acoustic signatures. Some sound like gentle chirps, others like dramatic whoops, and still others like complex songs with multiple harmonics and overtones. As our detectors become more sensitive and we learn to listen more carefully to the universe's gravitational wave symphony, we're discovering that the cosmos is far more musical than we ever imagined. Every massive object in the universe contributes to this cosmic orchestra, creating sounds that tell the stories of stellar birth, life, and death on scales that dwarf anything we can experience on Earth. The universe, it turns out, has been singing to us all along. We just needed to learn how to listen. Imagine, if you will, placing your hand gently on the chest of a sleeping giant. Feel that steady, powerful rhythm beneath your palm, the heartbeat that has been constant for millions of years. This is what it would be like to touch the surface of our sun, to feel the incredible vibrations that pulse through its massive body every few minutes, creating what astronomers lovingly call stellar oscillations. These oscillations are not the chaotic thrashing of a dying creature, but rather the most beautiful, organized symphony you could ever imagine. Deep within the sun's core, nuclear fusion creates enormous pressure waves that travel outward like ripples in a cosmic pond. But unlike the simple ripples we see when we drop a stone into still water, these waves are three-dimensional, complex, and utterly mesmerizing in their mathematical precision. The sun, you see, rings like a bell. Not just one bell, but thousands upon thousands of bells, each with its own unique tone and frequency. Some of these oscillations take just 5 minutes to complete their cycle, causing the sun's surface to rise and fall by mere meters, a tiny movement considering the sun's enormous size, yet detectable by our most sensitive instruments here on Earth. Picture the sun's surface as a vast ocean of plasma, hotter than any earthly fire, yet moving with the gentle rhythm of ocean swells on a calm day. In some places, the surface bulges outward ever so slightly, while in others it draws inward, creating patterns that shift and dance across the solar face like the most elegant ballet ever performed. These patterns tell us stories, incredible stories about what lies deep within our star's hidden interior. You see, as those pressure waves travel from the sun's core to its surface, they encounter different layers of varying temperature and density. Some waves speed up, others slow down, some bend and refract, others reflect back toward the center. It's as if the sun is singing to us, and each note carries information about the singer's anatomy. The low, deep tones come from oscillations that penetrate all the way to the sun's core, like the bass notes of a cathedral organ that rumble through your chest. These waves tell us about the nuclear furnace at the sun's heart, about the temperature and pressure in that unreachable realm where hydrogen atoms dance together to become helium, releasing the energy that warms our world. Higher frequency oscillations, meanwhile, are like the bright notes of a piccolo. They stay closer to the surface, giving us information about the sun's outer layers, its atmosphere, and the complex magnetic fields that create sunspots and solar flares. Together, these high and low frequencies create a chord so complex and beautiful that it would take a lifetime just to appreciate a single moment of the sun's song. What makes this even more remarkable is that we can actually hear echoes of this music here on Earth. Not with our ears, of course. Space is far too empty to carry sound waves in the traditional sense. But our instruments can detect the tiny changes in the sun's brightness and the subtle shifts in its gravitational field that these oscillations create. We have, in essence, learned to listen to starlight itself. The most incredible part is that every star sings its own unique song. A red giant star, swollen to hundreds of times our sun's size, oscillates much more slowly, like the deep, mournful tones of a whale song echoing through the cosmic ocean. Its surface rises and falls over the course of days or even weeks, creating a rhythm so slow and stately that it feels almost like breathing, the slow, patient breathing of an ancient being that has lived for billions of years. White dwarf stars, on the other hand, are like cosmic hummingbirds. These tiny, incredibly dense stellar remnants oscillate so rapidly that they create frequencies much higher than our sun's, pulsing every few seconds or minutes with clockwork precision. Their surfaces are so compact and their gravity so intense that even small oscillations create dramatic changes in brightness, turning these stellar corpses into cosmic lighthouses that flash their signals across the galaxy. And then there are the variable stars, the true virtuosos of the stellar orchestra. Stars like Cepheid variables expand and contract in regular cycles, their entire bodies swelling and shrinking like the chest of a singer taking breath for the next verse. As they expand, they cool and dim. As they contract, they heat up and shine more brightly. This creates a visual rhythm, a pulsing light that has served as a cosmic metronome, helping astronomers measure distances across the universe. Some of these variable stars are so regular in their pulsations that they rival the most precise clocks ever built by human hands. Others are more temperamental, their rhythms shifting and changing like a jazz musician improvising on a familiar theme. Each tells us something different about the physics of stellar interiors, about how stars balance the inward pull of gravity against the outward pressure of their own light and heat. The truly massive stars, those giants that will one day explode as supernovae, have their own unique acoustic signatures. Their oscillations are often more complex, more chaotic, as if these stellar titans are restless, unable to settle into the peaceful rhythms of smaller stars. This restlessness is prophetic, a sign of the incredible violence that awaits in their future. Their songs carry notes of instability, harmonics that speak of the nuclear battles raging in their cores as they struggle to fuse ever heavier elements. Scientists have discovered that we can actually predict how a star will die by listening to its current song. The frequencies and patterns of oscillation tell us about the star's mass, its age, its internal structure, and its likely fate. It's as if each star is singing its own requiem, years or even millions of years before its final performance. There's something deeply moving about the fact that our own sun has been singing to us every day of our lives, and yet most of us have never heard its voice. But in the 1960s, a curious astronomer named Robert Layton began to suspect that the sun might be talking to us in ways we had never imagined. He pointed his instruments at our nearest star and made a discovery that would revolutionize our understanding of stellar physics forever. What Layton found was that the sun's surface was moving, not the dramatic eruptions of solar flares or the slow rotation we had long known about, but a subtle, rhythmic motion that happened everywhere, all the time. The sun's face was rising and falling by just a few meters every 5 minutes, as if our star was gently breathing. This discovery launched the field of helioseismology, literally the study of sunquakes. Just as geologists use earthquakes to map the interior of our planet, astronomers realized they could use the sun's oscillations to create the first detailed maps of what lies beneath the solar surface. For the first time in human history, we could peer into the heart of a star. The sun's oscillations work much like the way sound travels through a musical instrument. When you pluck a guitar string, it vibrates at specific frequencies determined by the string's length, tension, and material. The sun, in essence, is like a three-dimensional guitar with millions of strings, each vibrating at its own frequency, creating a chord of such complexity that it contains virtually all the information about the sun's internal structure. But unlike a guitar, where we can see the strings directly, the sun keeps its secrets hidden beneath layers of blazing plasma. The oscillations we observe at the surface are like hearing a symphony from outside a concert hall. We can hear the music, but we have to work backwards to figure out what instruments are playing and how the concert hall itself shapes the sound. This detective work requires incredible patience and precision. Scientists must observe the sun continuously for months or years, measuring tiny changes in brightness and velocity across thousands of points on the solar surface. They track how different regions move up and down, how they speed up and slow down, creating vast maps of motion that reveal the hidden currents flowing beneath the sun's glowing face. What they found was breathtaking. The sun's interior is far more dynamic and complex than anyone had imagined. There are rivers of plasma flowing beneath the surface, circulating in patterns that dwarf any weather system on Earth. Some of these flows move from the equator toward the poles, others spiral in great vortices that can persist for years. There are layers within layers, each with its own temperature, density, and speed of rotation. Most remarkably, scientists discovered that different parts of the sun rotate at different speeds. The equator spins faster than the poles, but this differential rotation doesn't occur just at the surface. It extends deep into the sun's interior, creating a complex pattern of shear that generates the magnetic fields responsible for sunspots, solar flares, and all the other dramatic phenomena we observe in our star's atmosphere. The oscillations also revealed the location of the sun's energy source with unprecedented precision. Deep in the core, where the temperature reaches 15 million degrees Celsius, nuclear fusion transforms hydrogen into helium, releasing the energy that eventually reaches us as sunlight. But that energy doesn't travel directly from the core to the surface. It takes a random walk that can last hundreds of thousands of years, bouncing from atom to atom in a process so slow that the light warming your face today began its journey before humans walked the Earth. Helioseismology showed us exactly where this energy production occurs, confirming our theories about stellar fusion and revealing details about the sun's chemical composition that no other method could provide. The oscillations act like ultrasound waves in a medical examination, giving us a detailed picture of our star's anatomy without ever having to physically probe its interior. Perhaps most beautifully, scientists discovered that the sun's oscillations change over time in predictable patterns. During periods of high solar activity, when sunspots are numerous and solar flares are frequent, the oscillation frequencies shift slightly. It's as if the sun's mood affects its voice, making it sing in a slightly different key when it's feeling more energetic. This discovery opened up an entirely new way of monitoring solar activity and predicting space weather, the stream of charged particles and magnetic fields that the sun constantly sends into space. When these solar winds interact with Earth's magnetic field, they can create beautiful auroras, but they can also disrupt satellites, radio communications, and power grids. By listening to the sun's voice, we can now forecast these events with greater accuracy than ever before. The techniques developed for helioseismology have also been applied to other stars, giving birth to the broader field of astroseismology. Just as we learn to read the sun's interior structure from its oscillations, we can now peer inside distant stars, determining their masses, ages, sizes, and internal composition from their stellar songs. This has revolutionized our understanding of stellar evolution and helped us identify planets orbiting other stars. What makes this even more remarkable is that we're essentially doing archaeology with sound waves. The oscillations we observe today carry information about events that happened deep inside stars millions of years ago. Every frequency tells a story about nuclear reactions, convection currents, and magnetic fields that shaped the star's interior long before we were here to listen. In a sense, helioseismology has taught us that every star is like a time capsule, preserving in its oscillations the history of all the nuclear burning, mixing, and evolution that has occurred throughout its lifetime. We are learning to read these stellar memoirs written in the language of vibration and light, discovering the biographies of suns that have been singing their songs across the cosmos for billions of years. If you could somehow float in the void between galaxies and listen to the universe, you would hear the most extraordinary choir imaginable. Each star adds its own voice to this cosmic symphony, and no two voices are exactly alike. The diversity of stellar songs is as vast and beautiful as the diversity of life on Earth, with each type of star contributing its unique timbre to the greater harmony of space. Our sun, as we've discovered, is something like a steady baritone in this celestial choir, reliable, consistent, with a deep, warm tone that has remained essentially unchanged for billions of years. But venture to other corners of the galaxy, and you'll encounter voices of such variety and beauty that they would bring tears to your eyes if you could hear them with human ears. Consider the red giant stars, those ancient celebrities of the cosmos who have expanded to enormous sizes as they age. These stellar elders sing with voices so deep and resonant that their oscillations can take weeks to complete a single cycle. If our sun is a baritone, then red giants are the bass singers of the universe, their voices carrying the wisdom and weariness of eons. Betelgeuse, the red supergiant that forms the shoulder of the constellation Orion, is one of these cosmic bass singers. This magnificent star is so large that if it were placed at the centre of our solar system, its surface would extend beyond the orbit of Mars. Its oscillations are correspondingly grand. The entire star swells and contracts over periods of months or years, each breath causing brightness changes visible to the naked eye here on Earth. What makes Betelgeuse's song particularly poignant is that it carries the unmistakable notes of approaching death. This star is nearing the end of its life, and its oscillations are becoming increasingly irregular and unpredictable. Sometimes it dims dramatically, as if the singer is running out of breath. Other times it flares brighter, as if gathering strength for one final, glorious performance. Scientists believe that within the next few 100,000 years, a blink of an eye in cosmic terms, Betelgeuse will explode as a supernova, its final song echoing across the galaxy. At the opposite end of the spectrum are the white dwarf stars, the compressed remnants of stars like our Sun after they've shed their outer layers. These stellar corpses are about the size of Earth, but contain roughly the mass of our Sun, creating gravitational fields so intense that they warp space and time around them. Their oscillations are rapid and precise, like the quick, sharp notes of a piccolo. White dwarfs pulse every few seconds or minutes with clockwork regularity, their dense surfaces heating and cooling in response to the nuclear burning of material that has fallen onto them from space. Some white dwarfs are so regular in their pulsations that they rival the best atomic clocks ever built by humans. Others show complex patterns of oscillation that reveal the star's internal structure with incredible detail. Perhaps most fascinating are the white dwarfs that exist in binary systems, orbiting so close to a companion star that they steal material from their neighbour. As this stolen matter accumulates on the white dwarf surface, it eventually reaches a critical temperature and density, triggering a thermonuclear explosion that causes the star to brighten by thousands of times in a matter of hours. These events, called novae, are like cosmic hiccups, violent but not fatal, allowing the white dwarf to return to its steady pulsation until enough material accumulates for the next explosion. Then there are the neutron stars, the most extreme members of the stellar choir. These objects are the collapsed cores of massive stars that have undergone supernova explosions. They pack more mass than our Sun into a sphere only about 20 kilometers across, creating matter so dense that a teaspoon would weigh as much as a mountain on Earth. The oscillations of neutron stars are correspondingly extreme. They can spin hundreds of times per second, creating lighthouse-like beams of radiation that sweep across space. When these beams point toward Earth, we detect them as pulsars. Radio signals so regular that when they were first discovered in 1967, astronomers briefly wondered if they might be signals from alien civilizations. The truth turned out to be even more remarkable. These are the death songs of massive stars, their final messages transmitted across the cosmos with the precision of atomic clockwork. Some pulsars are gradually slowing down as they age, their songs deepening over millions of years like voices changing with time. Others are speeding up, fed by material falling from a companion star, their voices rising in pitch as they spin faster and faster. A few are so regular that they lose only 1 second every 10 million years, timing so precise that they're being used as cosmic GPS beacons to help navigate spacecraft across the solar system. The massive stars that will one day become neutron stars or black holes sing their own distinctive songs while they're still alive. These stellar giants are often unstable, their immense gravity barely balanced by the tremendous energy production in their cores. Their oscillations are irregular, chaotic, filled with the tension of impending catastrophe. They're like opera singers reaching for impossibly high notes, their voices straining with the effort, knowing that eventually their performance must end in dramatic fashion. Beta Cygni, a blue supergiant star, exemplifies this category. It pulsates irregularly over periods of hours to days, its brightness varying by small but measurable amounts as internal instabilities cause its outer layers to expand and contract. These variations are not smooth or predictable like those of our Sun, but rather jagged and erratic, as if the star is struggling to maintain its composure while enormous forces battle within its core. Variable stars of the Cepheid class represent perhaps the most musical members of the stellar choir. These stars oscillate with perfect regularity, expanding and contracting in cycles that can range from days to months. As they expand, they cool and dim. As they contract, they heat up and brighten. This creates a visual rhythm that's so regular and predictable that Cepheids have become the standard candles of astronomy, helping us measure distances across the universe. Delta Cephei, the prototype of this class, completes one oscillation cycle every 5.4 days with clockwork precision. Its surface temperature varies by about 1,500 degrees Celsius during each cycle, and its diameter changes by about 2 million kilometers, a pulsation so large that it would be clearly visible if we could watch from a nearby star system. The mathematical beauty of Cepheid oscillations is so perfect that they seem almost artificial, as if the universe itself is keeping time to some cosmic metronome. What makes the stellar choir even more remarkable is that we're learning to distinguish not just the primary voices of individual stars, but also their harmonics and overtones. Just as a violin note contains not just the fundamental frequency, but also a series of higher frequencies that give the instrument its distinctive timbre, stellar oscillations include complex patterns of higher order modes that reveal incredible detail about the star's internal structure. Modern space telescopes like Kepler and TESS have given us the ability to monitor thousands of stars simultaneously, creating the first comprehensive catalogue of stellar voices. We can now study the oscillations of stars across the entire galaxy, comparing young stars with old ones, small stars with large ones, solitary stars with those in binary systems. Each comparison teaches us something new about how stars are born, how they live, and how they die. The most beautiful music ever composed is playing all around us, every moment of every day, yet most of us will live our entire lives without ever hearing a single note. This is the cosmic symphony of stellar oscillations, gravitational waves, and electromagnetic radiation that fills the universe with sound. Not sound as we know it, but something far more profound and fundamental. The challenge of detecting stellar oscillations is like trying to hear a whisper in a thunderstorm while standing 1,000 miles away. The changes in starlight caused by stellar pulsations are often less than 1 part in a million, variations so tiny that they would be completely invisible to the naked eye. To detect these minute changes requires instruments of extraordinary sensitivity and techniques of breathtaking ingenuity. Imagine trying to measure the height of a person standing on the moon by looking at them through a telescope from Earth, and you'll have some sense of the precision required. The surface of our Sun rises and falls by only a few meters during its oscillations, a tiny movement compared to the Sun's diameter of 1.4 million kilometers. Yet scientists have developed methods to measure these microscopic changes with stunning accuracy. The key breakthrough came with the development of Doppler spectroscopy, a technique that measures the tiny shifts in starlight frequency caused by the motion of the star's surface. When part of a star's surface moves toward us, the light becomes slightly bluer. When it moves away, the light becomes slightly redder. These color changes are far too small to see directly, but sensitive instruments can detect frequency shifts, equivalent to a person walking at a leisurely pace. The process requires patience that would challenge a saint. To map a star's oscillations accurately, astronomers must observe continuously for months or years, collecting millions of individual measurements and looking for patterns in what initially appears to be random noise. It's like listening to a faint radio station through heavy static, gradually filtering out the interference until the music becomes clear. Ground-based observatories face additional challenges. Earth's atmosphere is constantly moving, causing starlight to twinkle and blur. Temperature changes, wind currents, and atmospheric turbulence all introduce noise that can mask the subtle signals scientists are trying to detect. It's rather like trying to hear a delicate piano piece while standing next to a busy highway. To overcome these limitations, astronomers have taken their instruments into space. The Kepler Space Telescope, launched in 2009, revolutionized the field of asteroseismology by providing incredibly stable, continuous observations of thousands of stars simultaneously. Free from atmospheric interference, Kepler could detect brightness variations as small as a few parts per million, sensitive enough to spot the oscillations of stars hundreds of light years away. Kepler's method was elegantly simple yet powerfully effective. It stared at the same patch of sky for over 4 years, measuring the brightness of more than 150,000 stars every 30 minutes. The resulting dataset contained billions of individual measurements, creating the most comprehensive survey of stellar oscillations ever assembled. For the first time, scientists could study the acoustic properties of stars across a wide range of masses, ages, and evolutionary stages. The data revealed patterns of stunning beauty and complexity. Some stars showed simple regular oscillations reminiscent of a tuning fork. Others displayed intricate patterns with dozens of simultaneous frequencies, like a full orchestra playing a complex symphony. Still others showed oscillations that changed over time, their frequencies slowly drifting as the stars evolved. One of the most remarkable discoveries was that stellar oscillations follow mathematical relationships that are universal across all types of stars. The spacing between oscillation frequencies depends on fundamental properties like the star's mass and size in ways that are remarkably similar to the mathematical relationships that govern musical instruments. It's as if the universe itself is constructed according to musical principles. Modern ground-based telescopes have also made extraordinary advances. Networks of observatories around the world now work together to provide continuous monitoring of the sun's oscillations, with one telescope taking over as Earth's rotation carries another into daylight. This global collaboration has created an uninterrupted record of solar oscillations spanning decades, revealing long-term changes in our star's behavior that would be impossible to detect from any single location. The precision of these measurements is almost beyond comprehension. Scientists can now detect velocity changes on the sun's surface of less than 1 centimeter per second, slower than a crawling baby. They can measure temperature variations of thousandths of a degree and track the motion of features smaller than individual states on the solar surface. But perhaps the most exciting development is the detection of gravitational waves, ripples in space-time itself created by the most violent events in the universe. When two black holes collide or when a massive star collapses in a supernova explosion, they create disturbances in the fabric of space and time that travel outward at the speed of light. These gravitational waves are, in a very real sense, the sound that cataclysmic stellar death makes. The Laser Interferometer. Gravitational Wave Observatory LIGO achieved the first direct detection of gravitational waves in 2015, opening an entirely new window into the universe. The signal came from two black holes spiraling into each other 1.3 billion years ago, creating a chirp-like pattern as their orbital frequency increased just before they merged. This brief signal, lasting only a fraction of a second, carried more information about the nature of black holes than centuries of optical astronomy had provided. Gravitational wave detectors are perhaps the most sensitive instruments ever built by humans. They can detect changes in distance smaller than 1/10,000th the width of a proton, a precision that would be equivalent to measuring the distance to the nearest star to within the width of a human hair. When a gravitational wave passes through the detector, it literally stretches and compresses space itself, changing the length of the detector arms by amounts so tiny they challenge our understanding of measurement itself. What makes gravitational waves particularly exciting is that they carry information that cannot be obtained any other way. Light can be absorbed, scattered, or blocked by intervening matter, but gravitational waves pass through everything. Planets, stars, entire galaxies, essentially unchanged. They provide a direct connection to the most extreme environments in the universe, places where matter and energy exist in states that cannot be replicated in any earthly laboratory. Each gravitational wave detection is like receiving a message from the universe's most violent moments, the final seconds of a massive star's life, the merger of neutron stars, or the collision of black holes. These signals tell us not just that these events occurred, but exactly how they unfolded, what masses were involved, and what the resulting objects looked like after the violence ended. Scientists are now developing even more sensitive detectors that will be able to hear the gravitational wave background of the universe, the accumulated whispers of countless stellar deaths and cosmic collisions that have occurred throughout cosmic history. This background radiation will be like the universe's memory, preserving in its subtle fluctuations the record of every dramatic stellar finale that has ever taken place. The combination of traditional astronomy, asteroseismology, and gravitational wave detection is creating a new kind of cosmic awareness. We are learning to listen to the universe in ways that our ancestors could never have imagined. Hearing the songs of stars and the death cries of black holes, with instruments that detect the most subtle vibrations in light, matter, and space-time itself. As we drift deeper into the cosmic concert hall, we begin to notice something profound about the star's melodies. Like a musician who ages with their instrument, a star's song transforms throughout its lifetime, growing richer, more complex, and ultimately more dramatic as it approaches its final performance. The gentle hum we've been listening to is just the beginning of a much grander composition. Imagine, if you will, a talented singer in their youth. Their voice is clear, steady, and pure. They can hold a note for what seems like forever, their tone unwavering and bright. This is our main sequence star, our sun in its prime, singing its hydrogen-burning song with the confidence of billions of years ahead. The nuclear fusion in its core creates a steady rhythm, a reliable beat that has kept time for nearly 5 billion years. The sound waves generated by this fusion travel outward, carrying the star's youthful energy in acoustic vibrations that would take 100,000 years to reach the surface if they could travel unimpeded. But as any musician knows, time changes everything. As hydrogen fuel begins to dwindle in the star's core, like a singer's breath growing shorter, the stellar song begins to shift. The core contracts slightly, heating up, and the fusion reactions become more intense. It's as if our cosmic singer is putting more effort into each note, their voice growing stronger but also more strained. The frequency of the star's oscillations begins to change, creating subtle variations in the stellar melody that astronomers can detect with their sensitive instruments. This transformation doesn't happen overnight. For a star like our Sun, this gradual change in song unfolds over hundreds of millions of years. The stellar oscillations, those pressure waves that create the star's music, begin to shift in frequency. Where once they vibrated at a steady 5-minute rhythm, now the patterns become more complex. Some frequencies grow stronger, others fade away, and new harmonics emerge that weren't there before. It's like listening to a familiar song being played in a different key, recognizable but somehow transformed. The helium that has been quietly building up in the core from billions of years of hydrogen fusion begins to play its own role in this cosmic symphony. Like sediment settling in a musical instrument, it changes the star's acoustics. The sound waves that once travelled freely through the hydrogen-rich core now encounter regions of different density, different composition. They bounce and refract, creating complex interference patterns that add new layers to the stellar song. Scientists have learned to read these changing melodies like a musical score written in the language of physics. By carefully listening to how a star's oscillations shift over time, they can peek inside the stellar interior, understanding what's happening in regions that light takes thousands of years to escape. It's like being able to see inside a piano while it's being played, watching the hammers strike the strings and observing how each component contributes to the final sound. As the star ages further, approaching the end of its main sequence lifetime, the changes become more dramatic. The hydrogen in the core becomes scarce, like a fireplace running low on fuel. The nuclear fires that have burned steadily for billions of years begin to flicker and fade in the very centre of the star. But stars, like determined musicians, don't give up easily. When the core hydrogen is finally exhausted, the star begins to burn hydrogen in a shell around the inert helium core, creating a new kind of stellar music. This shell burning is different from the core burning that dominated the star's main sequence life. It's less stable, more variable, like a singer who can no longer rely on their diaphragm and must use different muscles to produce their voice. The energy output becomes uneven, pulsing rather than steady. The star's surface begins to expand and cool, and its colour shifts from the hot white or yellow of its youth toward the cooler red of its approaching old age. The acoustic properties of the star change dramatically during this transition. The stellar oscillations that once had periods of just a few minutes now stretch to hours or even days. It's as if time itself is slowing down in the stellar symphony. The sound waves have much farther to travel as the star swells, and they encounter new regions of different temperature and density. Some frequencies that were once prominent fade away entirely, while others, previously salient, begin to emerge. For stars more massive than our Sun, this transformation happens more quickly and dramatically. A star 20 times the mass of the Sun might live only 10 million years compared to the Sun's 10 billion year lifetime, but their stellar song goes through even more dramatic changes. These massive stars burn through their nuclear fuel, like rock stars living fast and bright, their music more intense, more complex, and ultimately more spectacular in its finale. The acoustic signatures of these massive stars reveal the furious pace of their nuclear burning. Where the Sun fuses hydrogen at a steady rate, these stellar giants burn their fuel with such intensity that their cores go through multiple phases of nuclear fusion. After hydrogen burning comes helium burning, then carbon, neon, oxygen, and finally silicon. Each phase creates its own acoustic signature, its own contribution to the stellar symphony. Imagine an orchestra where the different sections come in one by one, each adding their voice to a growing crescendo. First the strings playing the hydrogen-burning melody. Then the woodwinds join in with helium fusion harmonies. The brass section adds the powerful carbon-burning themes, while the percussion finally enters with the rapid-fire silicon-burning rhythms. But unlike a human orchestra where all the sections can play together, in a massive star, each nuclear burning phase happens in its own shell, creating a complex, layered structure with its own acoustic properties. As we continue our gentle journey through the lives of stars, we encounter one of the most dramatic and beautiful phases of stellar evolution, the red giant stage. If the main sequence phase is like a star's productive middle age, then the red giant phase is like a grand, sweeping aria sung by an aging opera singer who has developed a deeper, more resonant voice with decades of experience. Picture our Sun still billions of years in the future as it begins this transformation. The hydrogen in its core has been exhausted, converted into helium through billions of years of nuclear fusion. The core, now composed mainly of helium, begins to contract under its own gravity. As it shrinks, it heats up like a bicycle pump getting warm when you compress air quickly. This heating ignites hydrogen fusion in a shell around the inert helium core, creating a new source of energy that actually produces more power than the star generated during its main sequence lifetime. This shell burning is inherently unstable, like trying to maintain a campfire with kindling arranged in a thin ring rather than a solid pile of logs. The energy production fluctuates, creating pulses of energy that travel outward through the star's layers. These pulses cause the star's outer layers to expand dramatically, like a balloon being inflated. The star's surface moves farther and farther from its core as it swells to enormous proportions. The acoustic properties of this expanding star change in fascinating ways. Remember how we talked about sound waves taking different amounts of time to travel through materials of different densities? Well, as the red giant expands, its outer layers become incredibly tenuous, thousands of times less dense than water, less dense even than the best vacuum we can create on Earth. Sound waves that once took minutes to travel from the stellar interior to the surface now take hours or even days. The star's oscillations slow down dramatically, like a giant bell whose deep tones ring out much more slowly than a small chime. Where main sequence stars like our current Sun oscillate with periods of about 5 minutes, red giant stars can have oscillation periods measured in days or even weeks. These slow, deep vibrations create a bass note in the cosmic symphony, a profound rumbling that speaks of the star's enormous size and the vast distances its sound waves must travel. But the red giant's song is not just slow and deep, it's also incredibly complex. The star's interior now has a layered structure, like a Russian nesting doll, with different regions having different compositions, temperatures, and densities. The inert helium core sits at the center, surrounded by a hydrogen-burning shell, which is itself surrounded by the star's expanded envelope of mainly hydrogen and helium. Each of these layers affects the sound waves differently. Some frequencies can penetrate deep into the star's interior, probing the helium core and revealing its properties through their acoustic signatures. Other frequencies are trapped in the star's outer layers, bouncing back and forth in the expanded envelope like sound waves in a cathedral. Still others get caught in the hydrogen-burning shell, their energy absorbed and re-emitted in complex patterns that create interference patterns throughout the stellar interior. The result is a rich, complex acoustic spectrum that tells the story of the star's internal structure in exquisite detail. Modern astroseismology can detect these different modes of oscillation and use them to map the interior of red giant stars with remarkable precision. We can determine the size of the helium core, the thickness of the hydrogen-burning shell, and even detect the presence of rotation in the star's deep interior. For stars like our Sun, the red giant phase is a time of relative stability, albeit with some dramatic changes. The star might pulsate gently, its surface moving in and out like slow breathing, creating variations in its brightness and acoustic output. These pulsations are driven by the same kinds of pressure waves we've been discussing, but now they operate on a much larger scale and with much longer periods. Some red giant stars develop complex patterns of oscillation that create what astronomers call mixed modes. These are acoustic waves that behave like pressure waves in the star's outer layers, but like gravity waves in the inner regions. They are particularly sensitive to the properties of the helium core, making them valuable probes of the star's deep interior. It's like having a musical note that changes pitch as it travels through different parts of an instrument, revealing information about each section it passes through. The acoustic signatures of red giant stars have revealed some surprising discoveries. For instance, scientists have found that the cores of red giant stars rotate much more slowly than their outer layers, suggesting that some mechanism is acting to slow down the core's rotation as the star evolves. This was a completely unexpected finding that has forced astronomers to revise their understanding of how angular momentum is transported within evolving stars. But perhaps the most remarkable aspect of red giant stars is how their acoustic properties prepare us for what's to come. As we listen to their slow, deep oscillations, we're hearing the prelude to the star's final act. The red giant phase is not the end of the stellar story, it's the dramatic build-up to the finale. The star is gathering energy, expanding its stage, and preparing for the climactic moments that will define its ultimate fate. For lower mass stars like our Sun, the red giant phase will eventually lead to a helium flash, a sudden ignition of helium fusion in the core that will transform the star once again. For more massive stars, the red giant phase is just the first movement in a symphony that will include multiple episodes of expansion and contraction, each creating its own unique acoustic signature as the star burns through progressively heavier elements in its core. As we stand in our cosmic concert hall, listening to the deep, resonant voices of red giant stars, we're witnessing one of the most beautiful and complex phases of stellar evolution. These aging stars, swollen to enormous sizes, ping their arias with voices that span octaves we never heard during their main sequence youth. Their songs are filled with the complexity of their layered interiors, the drama of their unstable energy production, and the poignancy of their approaching transformation. As we prepare to witness the final movements of the cosmic symphony, we must understand that not all stars face the same fate. Like different musical instruments, stars of different masses create different kinds of endings to their songs. The way a star dies, and the sounds it makes in those final moments, depends largely on how much matter it contains when it first begins to shine. Imagine a cosmic orchestra where the instruments are sorted not by type but by size. The smallest instruments, like our Sun and smaller stars, are like delicate flutes or violins. They produce beautiful clear notes throughout their long lives, but when they reach their final performance, their endings are relatively gentle, like a song that fades to a whisper. These low-mass stars, those with less than about 8 times the mass of our Sun, will eventually exhaust their nuclear fuel and end their lives as white dwarf stars, tiny but incredibly dense remnants that slowly cool over trillions of years. The acoustic signature of a dying low-mass star is remarkably different from the steady oscillations of its main sequence youth. As these stars progress through their red giant phase, they begin to lose mass through stellar winds, streams of particles that flow away from the star's surface like a gentle breeze. These winds affect the star's acoustic properties, creating new kinds of oscillations and changing the way sound waves propagate through the stellar material. The mass loss process itself creates its own kind of sound. As material flows away from the star, it carries with it magnetic fields and creates shock waves in the surrounding space. While these shock waves can't propagate a sound in the vacuum of space, they do create electromagnetic signals that our instruments can detect. It's like hearing the echo of a conversation in a room next door. We can't hear the original voices, but we can detect the vibrations they create. When a low-mass star finally exhausts its nuclear fuel, it doesn't explode dramatically. Instead, it gently sheds its outer layers, creating a beautiful planetary nebula, a glowing shell of gas illuminated by the hot tiny white dwarf that remains at the center. The acoustic story of this process is one of gradual quieting, like a song that slowly fades until only the final note remains, held by the white dwarf as it slowly cools over cosmic time, but move up in stellar mass, and the story becomes dramatically different. Stars between about 8 and 25 times the mass of our Sun are like the brass section of our cosmic orchestra, powerful, resonant, and capable of producing incredibly dramatic finales. These stars live fast and die spectacularly, their lives compressed into mere millions of years compared to the billions of years enjoyed by smaller stars. The acoustic signatures of these massive stars reveal the furious pace of their nuclear burning. Their cores cycle through different nuclear fuels like a race car shifting gears, each phase creating its own unique oscillation patterns. After exhausting hydrogen in their cores, they burn helium, then carbon, then neon, oxygen, and finally silicon. Each burning phase happens faster than the last, creating an acoustic crescendo that builds toward the star's explosive finale. The silicon burning phase is particularly dramatic from an acoustic perspective. Silicon nuclei fuse together in complex chains of reactions that eventually produce iron. But iron is special. It's the most stable nucleus in the universe. When a star tries to fuse iron nuclei together, instead of releasing energy, the reaction actually absorbs energy. It's like trying to get a fire to burn water. Not only does it not work, but it actually puts out the fire. As iron builds up in the core of a massive star, the nuclear fires that have supported the star against gravity for millions of years suddenly go out. The core, no longer supported by the outward pressure of nuclear fusion, collapses catastrophically. In less than a second, a core the size of Earth shrinks to a sphere only about 12 miles across. The acoustic signature of this collapse is unlike anything else in the universe. Imagine the sound of every building in a city collapsing simultaneously, compressed into a fraction of a second. The core collapse of a massive star releases more energy in gravitational waves and neutrinos than our Sun will produce in its entire 10 billion year lifetime. The collapse is so rapid and so violent that it creates ripples in space-time itself, gravitational waves that carry the acoustic signature of the stellar death across the universe at the speed of light. But the collapse doesn't happen in silence. As the core implodes, it reaches nuclear density, the same density as the nucleus of an atom. At this point, the strong nuclear force that holds atomic nuclei together suddenly becomes repulsive, like a compressed spring that's been pushed to its limit. The collapsing core bounces, sending a shock wave racing outward through the star at thousands of miles per second. This shock wave is the cosmic equivalent of a sonic boom, but instead of being created by an object moving faster than sound, it's created by the sudden release of gravitational energy from the core collapse. As the shock wave travels outward through the star's layers, it encounters different densities and compositions, creating complex acoustic patterns that reveal the star's internal structure in its final moments. The shock wave doesn't travel smoothly through the star. Instead, it encounters layers of different elements left behind by the star's previous nuclear burning phases. each layer affects the shockwave differently, creating a complex pattern of acceleration and deceleration. In some regions, the shockwave speeds up. In others, it slows down or even stalls temporarily. These variations create acoustic oscillations that can be detected in the light emitted by the explosion. When the shockwave finally reaches the star's surface, it blows the outer layers into space in a titanic explosion called a supernova. The energy released in this explosion is so enormous that it can briefly outshine an entire galaxy containing hundreds of billions of stars. But from an acoustic perspective, what's most remarkable is that the explosion carries with it the acoustic signature of the star's final moments, encoded in the patterns of elements dispersed into space and the gravitational waves rippling away from the explosion site. The most massive stars, those with more than about 25 times the mass of our Sun, face an even more dramatic fate. Their cores are so massive that not even the nuclear force can halt their collapse. These stars become black holes, regions of space-time where gravity is so strong that not even light can escape. The acoustic signature of black hole formation is perhaps the most extreme in the universe, a gravitational wave signal that carries the sound of space-time itself being torn and reformed. Recent detections of gravitational waves from colliding black holes have given us our first direct listening experience of these cosmic catastrophes. The sound of two black holes spiraling into each other and merging is like a cosmic chirp, rising in frequency and amplitude before cutting off abruptly when the new, larger black hole settles into its final configuration. It's a sound that represents the ultimate transformation of matter and energy, the final note in the most massive star's cosmic symphony. But even black holes aren't completely silent. Stephen Hawking discovered that black holes actually emit radiation, slowly evaporating over time. This Hawking radiation carries with it information about the black hole's properties, creating a kind of acoustic signature that will persist for trillions upon trillions of years as the black hole slowly returns its mass energy to the universe. As we stand in our cosmic concert hall, having listened to the gentle oscillations of main sequence stars and the complex harmonies of red giants, we can sense that something extraordinary is building. The stellar songs around us are growing more intense, more complex, more urgent. Like an orchestra preparing for the climactic movement of a symphony, the stars are gathering their energy for the most dramatic performances of their lives. The acoustic signatures we've been following tell us that we're approaching the moments when stars exhaust their ability to sustain themselves through nuclear fusion. For billions of years, these cosmic musicians have maintained their songs through the delicate balance between the inward pull of gravity and the outward pressure of nuclear fire. But now, that balance is about to be broken, and the consequences will create the most spectacular sounds in the universe. In the red giant stars around us, we can hear the acoustic signatures of cores that are running out of fuel. The helium that has been accumulating for billions of years is beginning to reach the temperatures and pressures needed for fusion. But helium fusion is different from the hydrogen burning that has sustained these stars for so long. It's more temperamental, more explosive, more prone to dramatic fluctuations that create complex acoustic patterns. For stars like our Sun, this helium fusion will begin with what astronomers call the helium flash, a sudden, violent ignition of helium burning in the core. From an acoustic perspective, this event is like the difference between lighting a candle and setting off a firecracker. The helium flash releases enormous amounts of energy in a very short time, creating shockwaves that propagate throughout the star's interior. The acoustic signature of a helium flash is remarkably complex. The sudden energy release creates a burst of high-frequency oscillations that travel outward through the star's layers. These waves encounter the different density regions we have discussed: the helium core, the hydrogen-burning shell, the expanded envelope, and each region affects the waves differently. Some frequencies are absorbed, others are reflected, and still others are amplified through resonance effects. The result is a cacophony of acoustic activity that gradually settles into new patterns as the star adjusts to its new energy source. The helium-burning core creates different oscillation patterns than the hydrogen-burning core that preceded it. The frequencies are different, the amplitudes are different, and the way the waves interact with the star's outer layers is different. It's like listening to the same musician switch from playing a piano to playing an organ. The basic musical skills are the same, but the instrument produces an entirely different sound. But the helium flash is just the beginning of the crescendo for lower mass stars. As these stars burn helium in their cores, they continue to burn hydrogen in a shell around the core. This double burning creates a complex acoustic environment with multiple sources of oscillation. The helium-burning core produces its own set of pressure waves, while the hydrogen-burning shell creates another set. These waves interfere with each other, creating beat patterns and resonances that make the star's acoustic signature incredibly rich and complex. For more massive stars, the crescendo is even more dramatic. These stellar giants don't just burn helium after hydrogen, they continue through a series of nuclear burning phases, each more intense than the last. Carbon burning follows helium burning, then neon burning, then oxygen burning, and finally silicon burning. Each phase happens faster than the previous one, creating an accelerating acoustic crescendo that builds toward the star's explosive finale. The acoustic signatures of these multiple burning phases are like listening to a complex piece of music with multiple themes playing simultaneously. Each nuclear burning process creates its own characteristic frequency patterns, its own acoustic fingerprint. The carbon-burning core might oscillate at one set of frequencies, while the helium-burning shell oscillates at another, and the hydrogen-burning shell at yet another. The result is a polyphonic stellar song with multiple voices singing different parts of the same cosmic composition. As we listen more carefully to these massive stars approaching their final moments, we can hear something else in their acoustic signatures: instability. The nuclear burning processes become increasingly difficult to sustain as the star moves up the periodic table to heavier and heavier elements. The energy released per fusion reaction decreases, making it harder for the star to maintain the outward pressure needed to resist gravity. This instability manifests acoustically as irregular oscillations, sudden changes in frequency and amplitude, and the appearance of new acoustic modes that weren't present in the star's younger days. It's like listening to a singer who is struggling to maintain their voice, with occasional cracks and wavers that suggest they're approaching their limits. The star's acoustic signature becomes more chaotic, more unpredictable, more urgent. The silicon burning phase, the final nuclear burning process in massive stars, creates particularly distinctive acoustic patterns. Silicon fusion produces iron, and as iron accumulates in the core, the star's acoustic properties change dramatically. Iron nuclei are much more massive than the lighter elements that preceded them, and they affect the propagation of sound waves through the stellar core in unique ways. The growing iron core creates an acoustic barrier of sorts. Sound waves that could easily penetrate the lighter elements of previous burning phases find it increasingly difficult to propagate through the iron-rich core. Some frequencies are completely blocked, creating acoustic shadows in the star's interior. Other frequencies are reflected back, creating standing wave patterns that can build up to enormous amplitudes. As the iron core grows, approaching the critical mass that will trigger core collapse, the star's acoustic signature becomes increasingly ominous. The normal oscillation patterns become disrupted as the core's properties change. New acoustic modes appear, driven by the instabilities in the nuclear burning processes. The star begins to pulsate irregularly, its surface brightness varies, fluctuating as internal pressure waves reach the stellar surface. But for the most massive stars, this phase can last only days or weeks. The acoustic signature changes almost hourly as the core approaches its critical mass. It's like listening to a countdown in a language made of sound waves, with each acoustic change marking the star's approach to its final moment. The frequencies shift, the amplitudes grow, and the complexity increases as the star prepares for the most dramatic acoustic event in the universe: core collapse and supernova explosion. But even as we anticipate these spectacular stellar deaths, we must remember that the universe is vast, and stellar death is just one movement in the cosmic symphony. The elements forged in the cores of dying stars, The carbon, oxygen, silicon, and iron that will be dispersed into space by supernovae will become the building blocks of new stars, new planets, and perhaps new forms of life. The acoustic energy released by stellar death will propagate across the galaxy, influencing the formation of new stars and continuing the cosmic cycle of creation and destruction. As we prepare to witness these final stellar performances, we do so with the knowledge that we are not just observers but participants in this cosmic symphony. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these elements were forged in the cores of stars and dispersed by the violent acoustic events we are about to witness. In a very real sense, we are made of stardust, and the sounds we are about to hear are the echoes of our own cosmic origin story. As we journey deeper into the heart of stellar death, we arrive at moments so profound that they reshape our understanding of what it means to truly hear the universe. The gentle hums and whispers we've been following through a star's lifetime are about to transform into something far more dramatic, far more beautiful, and far more haunting than anything we could have imagined. Picture, if you will, a massive star in its final days. This isn't our gentle sun, but a giant perhaps 20, 30, or even 50 times more massive. For millions of years, Ithacan has been burning through its nuclear fuel with the intensity of a cosmic furnace, creating elements heavier and heavier in its core. Iron, cobalt, nickel, the building blocks of planets and life itself are being forged in temperatures that would make our sun seem like a cool summer breeze. But here's where the story takes a dramatic turn. Iron, you see, is different from all the other elements a star has been creating. When a star fuses hydrogen into helium, or helium into carbon, or carbon into oxygen, it releases energy. This energy pushes outward, fighting against the relentless pull of gravity that wants to crush the star into nothingness. It's been a delicate dance, this balance between the outward pressure of nuclear fusion and the inward pull of gravity, played out over cosmic timescales. Iron changes everything. When a star tries to fuse iron into heavier elements, something remarkable happens. Instead of releasing energy, it absorbs energy. Suddenly, the star's core begins to cool. The outward pressure that has been holding the star up for millions of years starts to weaken. Gravity, patient and persistent, finally begins to win. What happens next unfolds in a matter of seconds, but those seconds contain some of the most violent and beautiful events in the entire universe. The core, no longer supported by the energy of fusion, begins to collapse. Not slowly, not gradually, but with a speed that defies imagination. In less than a second, a core the size of Earth compresses to a sphere only 12 miles across. The density becomes so extreme that a teaspoon of this matter would weigh as much as a mountain. This is where the sound, the true sound, begins to emerge. As the core collapses, it doesn't just compress, it rebounds. The infalling matter hits this incredibly dense core and bounces back outward with tremendous force. This creates a shockwave that propagates through the star's outer layers, heating them to billions of degrees and accelerating them to speeds of thousands of miles per second. Now, you might wonder, how can this create sound when we've established that space is essentially silent? The answer lies in something far more subtle and profound than the pressure waves we call sound here on Earth. The collapsing core and the resulting explosion create ripples in the very fabric of space-time itself. These are gravitational waves, the universe's true voice, speaking in a language that transcends the need for any medium to carry it. When that massive core collapses, it doesn't just compress matter, it compresses space and time themselves. Einstein predicted this over a century ago, but it's only recently that we've developed the technology sensitive enough to hear these cosmic whispers. The gravitational waves produced by a collapsing stellar core are like the universe's own heartbeat, pulsing outward at the speed of light, carrying with them the story of that star's final moments. The frequency of these gravitational waves tells us an incredible story. As the core collapses, the waves begin at frequencies we might recognize. perhaps a few hundred cycles per second, like the deeper notes of a piano. But as the collapse accelerates and the core becomes more compact, the frequency rises. It's like listening to a cosmic Doppler effect. But instead of a train whistle changing pitch as it passes by, we're hearing the fundamental structure of reality itself being stretched and compressed. The amplitude of these waves, their strength, tells us about the mass of the collapsing core. A more massive core creates stronger gravitational waves, like a larger stone creating bigger ripples in a pond. But unlike ripples in water, these waves in space-time can travel across billions of light-years without losing their essential character. They carry the signature of that dying star's final moments across the cosmos, a message in a bottle cast into the vast ocean of space and time. The explosion that follows the core collapse is what we call a supernova, and each type creates its own unique acoustic signature in the gravitational wave spectrum. Let me paint you a picture of these cosmic symphonies, each as unique as a fingerprint, each telling a different story of stellar death. First, there are the Type II supernovae, the deaths of the massive stars we've been following. These are perhaps the most dramatic performers in our cosmic orchestra. When that shockwave rebounds from the collapsed core, it doesn't just create gravitational waves, it creates a cacophony of activity that would make the most complex symphony seem simple by comparison. The initial collapse creates a burst of gravitational waves that lasts only milliseconds, but within those milliseconds, the frequency sweeps across a range that tells us everything about the star's final moments. Scientists who study these waves describe them as chirps, a rapid increase in frequency that sounds almost like a bird's call when converted to audio frequencies we can hear. But this is a bird call that contains the compressed history of millions of years of stellar evolution. As the shockwave propagates outward through the star's layers, it encounters different densities of material. Each layer has its own acoustic properties, its own way of responding to the tremendous forces being unleashed. The hydrogen-rich outer envelope of the star responds differently than the helium-rich layer beneath it. The carbon and oxygen layers deeper still each have their own signature. It's like listening to a musical instrument where each string is made of different materials, each contributing its own unique tone to the overall sound. But the story doesn't end with the explosion. In many cases, the collapsed core becomes something called a neutron star, an object so dense that atomic nuclei are crushed together, creating a sphere of pure neutrons. These neutron stars are like cosmic bells, ringing with gravitational waves at frequencies determined by their mass, size, and spin rate. A newly formed neutron star is not a quiet object. It spins rapidly, perhaps hundreds of times per second, and its surface may be covered with mountains only inches high, but containing more mass than Mount Everest. As this object spins, any asymmetry in its shape creates a continuous stream of gravitational waves, like a cosmic lighthouse sweeping its beam across the universe. The pitch of these waves depends on the neutron star's rotation rate. A neutron star spinning 700 times per second would create gravitational waves at 1,400 Hz, about the frequency of a high-pitched musical note. But unlike a musical note that fades away, these gravitational waves can continue for thousands of years, as the neutron star slowly loses energy and spins down. Type Ia supernovae create an entirely different kind of cosmic music. These explosions occur when a white dwarf star, the compressed remnant of a star like our Sun, accumulates material from a companion star. When the white dwarf reaches a critical mass, it undergoes a thermonuclear explosion that completely destroys the star. There's no neutron star left behind, no ringing cosmic bell. Instead, we get a brilliant flash of gravitational waves that tells the story of complete stellar annihilation. The gravitational wave signature of a Type Ia supernova is more subtle than its Type II cousin. The explosion happens more gradually, and the gravitational waves are produced primarily by the asymmetric burning of nuclear fuel as the explosion propagates through the white dwarf. These waves carry information about the explosion mechanism itself, how the flame front moves through the star, how the star tears itself apart, how the energy is released in the final moments. What makes these signals particularly fascinating is their consistency. Type Ia supernovae are remarkably uniform in their properties, which is why astronomers use them as standard candles to measure distances across the universe. Their gravitational wave signatures should be similarly consistent, giving us a new way to study these cosmic explosions and understand the mechanisms that drive them. The frequency evolution of a Type Ia supernova's gravitational waves tells a story of accelerating destruction. As the explosion propagates outward, the burning material accelerates, creating waves at higher and higher frequencies. It's like listening to a cosmic engine revving up, building to a crescendo that ends not with a bang but with silence, the complete dissolution of a star that has given its last breath to the universe. Sometimes, the most massive stars don't explode at all. When a star is so large that even a supernova explosion cannot halt the gravitational collapse, something even more extraordinary happens. The core continues to collapse past the neutron star stage, past any known form of matter, until it becomes something that exists at the very edge of our understanding of physics, a black hole. The formation of a black hole is perhaps the most subtle sound in our cosmic symphony. As the stellar core collapses beyond the point of no return, it crosses what we call the event horizon, the boundary beyond which nothing, not even light, can escape. This transition happens quietly, almost whisperingly, marked by gravitational waves that start strong but quickly fade as the newly formed black hole settles into its final state. The gravitational wave signature of black hole formation is hauntingly beautiful in its simplicity. Unlike the complex, multi-layered sounds of supernovae, a forming black hole creates waves that follow a precise mathematical pattern. The frequency starts high and decreases exponentially, like a cosmic sigh as the black hole absorbs the last of the collapsing matter. This exponential decay is one of the most profound sounds in the universe because it represents the ultimate victory of gravity over all other forces. The waves are generated by the black hole's event horizon itself as it oscillates and settles into its final shape. Different modes of oscillation create different frequencies, like the various harmonics of a struck bell, but these are harmonics that fade away as the black hole reaches its equilibrium state. The mass of the black hole determines the frequency of these oscillations. A black hole with the mass of our Sun would oscillate at about 1,600 Hz, while a black hole 10 times more massive would oscillate at 160 Hz. These frequencies are encoded in the gravitational waves, allowing us to weigh the black hole simply by listening to its formation song. But black holes are not silent once they form. They continue to influence the cosmic soundscape in ways both subtle and dramatic. When matter falls into a black hole, it doesn't just disappear quietly. The process of accretion matter spiraling inward toward the event horizon creates its own gravitational wave signature. Imagine a small object, perhaps a chunk of matter from the original star, orbiting closer and closer to the black hole. As it spirals inward, it accelerates, and this acceleration creates gravitational waves. The frequency of these waves increases as the object moves faster and faster, creating another type of chirp signal, but this chirp is different from the one created during the initial collapse. It's more gradual, more sustained, like a cosmic slide whistle that can last for hours or even days. The most dramatic black hole sounds occur when two black holes collide and merge. These events, which we'll explore more deeply in our next chapter, create some of the most powerful gravitational wave signals in the universe. But even a solitary black hole, the remnant of a single massive star, continues to sing its quiet song as it interacts with the fabric of space-time around it. The space around a black hole is not empty. It's filled with subtle currents and eddies in the gravitational field. These perturbations create low-frequency gravitational waves that can persist for millions of years. They're incredibly faint, far below the sensitivity of our current detectors, but they represent a constant background hum in the universe's acoustic landscape. What's particularly fascinating about black hole formation is how it represents a phase transition in the sound of stellar death. Up until the moment the event horizon forms, The collapsing core creates gravitational waves that follow the laws of ordinary matter under extreme conditions. But once the black hole forms, the waves begin to follow the curved geometry of space-time itself. It's as if the universe switches from playing a material instrument to playing the very strings of reality. The mathematics that describe these black hole sounds are some of the most elegant in all of physics. They combine Einstein's general relativity with quantum mechanics in ways that reveal deep truths about the nature of space and time. The frequencies and decay rates of black hole oscillations are determined by fundamental constants of physics, the speed of light, the gravitational constant, and Planck's constant. In a very real sense, when we listen to a black hole's gravitational waves, we're hearing the universe speak in its most fundamental language. For most of human history, these cosmic sounds existed only in the realm of theory. Einstein himself doubted that gravitational waves would ever be detected. They seemed too weak, too subtle to ever register on any conceivable instrument. But human ingenuity has a way of exceeding even the boldest predictions, and today we have built instruments so sensitive that they can hear the universe's whispers from billions of light years away. The Laser Interferometer Gravitational Wave Observatory, or LIGO, represents one of the most ambitious scientific endeavours in human history. To understand how we detect these cosmic sounds, imagine trying to measure a change in distance smaller than 1/10,000th the width of a proton. That's the kind of sensitivity required to detect gravitational waves from dying stars. LIGO consists of two identical facilities, one in Louisiana and one in Washington state, each featuring two arms that stretch for 2.5 miles in perpendicular directions. Inside these arms, laser light bounces back and forth between mirrors, creating an interference pattern that can detect the tiniest changes in the arm's lengths. When a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction, causing the laser light to shift slightly and creating a detectable signal. The first gravitational waves detected by LIGO in September 2015 came not from a dying star, but from the collision of two black holes that had been spiraling around each other for billions of years. But this detection opened the door to a new era of astronomy, one where we don't just see the universe, but hear it as well. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Each one tells a unique story of cosmic catastrophe, and together they're building a comprehensive catalogue of the universe's most violent sounds. The data from these detections reads like a cosmic symphony program, with each event labelled by its date and character. GW150914, the first detection, was a short, sharp chirp lasting only about 0.2 seconds. The frequency swept from 35 Hz to 350 Hz, telling the story of two black holes, each about 30 times the mass of our Sun, spiralling together and merging into a single larger black hole. The sound, when played through speakers, resembles a bird's chirp, a rapid rise in pitch followed by sudden stop. But it's the detection of GW170817 that perhaps comes closest to the sounds we've been exploring, the sounds of dying stars. This event was different from the black hole mergers that LIGO had been detecting. It was the collision of two neutron stars, the dense remnants of massive stars that had died in supernova explosions millions of years earlier. The gravitational wave signal from GW170817 lasted much longer than the black hole mergers, about 100 seconds of detectable signal as the two neutron stars spiraled closer and closer together. The frequency started at just 24 Hz and rose to over 1000 Hz, creating an extended chirp that contained far more information than the brief signals from black hole mergers. What made GW170817 truly special was that it was accompanied by light. Unlike black holes, which emit no light when they merge, the the neutron-star collision created a brilliant flash of gamma rays, X-rays, and visible light. For the first time, astronomers could both hear and see the same cosmic event, opening up entirely new ways of studying the universe. The light from GW 170817 told us that neutron-star mergers are cosmic alchemists, forging heavy elements like gold and platinum in the extreme conditions of their collision. The gravitational waves told us about the fundamental properties of matter under conditions that can't be replicated in any laboratory on Earth. Together, they painted a complete picture of one of the universe's most spectacular events. The sensitivity of LIGO and Virgo continues to improve, and with each upgrade, we're able to hear fainter and more distant cosmic sounds. The next generation of gravitational wave detectors, already in development, will be able to detect the much weaker signals from individual supernova explosions. We're approaching a time when we'll be able to hear the death cry of every massive star in our local group of galaxies. But perhaps the most profound aspect of gravitational wave detection is how it has changed our relationship with the universe. For thousands of years, humans have gazed at the stars and wondered about their stories. Now, for the first time, we can actually hear those stories being told. The universe has found its voice, and we have finally learned to listen. As we near the end of our journey through the sounds of stellar death, we encounter some of the most spectacular and musically complex events in the universe, the collisions of neutron stars, which create explosions called kilonovae. These events represent the ultimate finale in the life cycle of binary star systems, where two massive stars have lived their entire lives in a cosmic dance, only to meet in a final, cataclysmic embrace. To understand the sound of a kilonova, we must first appreciate the incredible journey that leads to such an event. Two massive stars born from the same cosmic cloud spend millions of years orbiting each other. They age together, evolving from young, hot stars to red giants, and eventually both explode as supernovae. Remarkably, their gravitational bond survives even these explosive deaths, leaving behind two neutron stars locked in an ever-tightening orbital dance. Over millions or billions of years, this dance gradually spirals inward. The two neutron stars lose energy by emitting gravitational waves, a process so gradual that it would be imperceptible to any observer, but relentless in its cosmic patience. As they spiral closer, they begin to influence each other's shape, creating a gravitational tug-of-war that generates increasingly strong waves. The final moments of this billion-year courtship unfold with breathtaking speed. When the neutron stars are still hundreds of miles apart, they're already orbiting each other dozens of times per second. The gravitational waves they emit at this stage are like a cosmic drum roll, building in intensity and frequency as the final moment approaches. As the neutron stars draw closer, their gravitational fields begin to tear at each other's surfaces. Remember, these are objects so dense that a sugar cube-sized piece would weigh as much as a mountain. Yet even these incredibly dense objects begin to deform under the extreme tidal forces of their companion. The spherical neutron stars become egg-shaped, then more and more distorted as they spiral together. This deformation creates additional gravitational wave frequencies, harmonics that add complexity to the cosmic song. It's like listening to a musical instrument where the strings are being stretched and twisted even as they're being played. The gravitational wave signal becomes richer, more complex, carrying information about the internal structure of neutron stars, details about the nature of matter under the most extreme conditions in the universe. The final plunge happens in milliseconds. When the neutron stars are only a few miles apart, they're orbiting each other over 1,000 times per second. The gravitational waves at this point are shrieking at frequencies above 1,000 Hz, creating a cosmic crescendo that represents one of the most powerful events in the universe. The energy being radiated away in gravitational waves during these final moments exceeds the total light output of all the stars in the observable universe. The collision itself creates a gravitational wave signal unlike anything else in the universe. Unlike the simple chirp of a black hole merger, the neutron-star collision creates a complex symphony of different frequencies. There's the main chirp as the stars spiral together, but there are also higher frequency components created by the deformation and eventual destruction of the neutron stars themselves. When the neutron stars finally touch, the collision creates a shockwave that rips through both objects. Some of the matter from the neutron stars is ejected at high speed, creating a cloud of neutron-rich material that expands outward at thousands of miles per second. This ejected material is where some of the heaviest elements in the universe are born: gold, platinum, uranium, and other elements that can only be created in the extreme conditions of a neutron-star merger. The gravitational wave signature of this matter ejection is remarkably complex. Different models predict different patterns, but all involve rapidly oscillating gravitational fields that create waves at frequencies both higher and lower than the main merger signal. It's like listening to a cosmic explosion where different parts of the debris are creating their own acoustic signatures. What remains after the collision depends on the total mass of the two neutron stars. If they're not too massive, they might merge to form a single larger neutron star. This newly formed object would be highly unstable, oscillating violently and emitting gravitational waves at frequencies determined by its mass and internal structure. These post-merger oscillations can last for seconds or even minutes, creating a sustained gravitational wave signal that gradually fades as the neutron star settles into its new configuration. If the combined mass is too great, the merged object immediately collapses into a black hole. This creates yet another type of gravitational wave signal, the characteristic exponential decay we discussed earlier as the black hole settles into its final state. But this black hole is different from those formed by single stellar collapse. It's born surrounded by a disk of neutron-rich material, which continues to fall inward, creating additional gravitational waves that can persist for hours or days. The clonus explosion that follows the neutron star merger creates its own acoustic signature. As the ejected material expands and cools, it undergoes a complex series of nuclear reactions that power the optical light we see from these events. But the same processes that create the light also create subtle gravitational waves as the expanding material interacts with the curved space-time around the newly formed black hole or neutron star. These late-time gravitational waves are incredibly faint, far below the sensitivity of current detectors, but they represent a kind of cosmic echo, a reverberation of the original collision that can persist for years as the kilonova remnant continues to evolve. Future generations of gravitational wave detectors may be sensitive enough to detect these echoes, giving us an even more complete picture of these extraordinary events. The sound of a kilonova, when we convert the gravitational wave data to audio frequencies, is unlike anything in our earthly experience. It begins with a rising whine as the neutron stars spiral together, builds to a chaotic crescendo during the collision, and then fades into a complex mixture of tones as the remnant settles. It's simultaneously beautiful and terrifying, the universe's way of marking the end of a cosmic love story that has lasted billions of years. But perhaps most remarkably, the detection of kilonova gravitational waves has allowed us to solve one of the oldest mysteries in astronomy, the origin of the heavy elements. Every atom of gold in your jewelry, every atom of platinum in your car's catalytic converter was forged in the collision of two neutron stars somewhere in the universe. The gravitational waves from these collisions carry the acoustic signature of cosmic alchemy, the sound of the universe creating the elements that make planets and life possible. As we listen to these cosmic sounds, we're not just detecting gravitational waves, we're hearing the universe write its own history. Each kilonova represents a chapter in the story of how the cosmos has evolved from a simple soup of hydrogen and helium to the rich, complex universe we see today. The sounds of stellar death are, paradoxically, also the sounds of cosmic birth, the creation of new elements, new possibilities, new chapters in the ongoing story of the universe. And so we come to understand that the universe is not just a vast, silent expanse of space and time, but a living, breathing, singing cosmos, where every star has a voice and every death creates a new song. The sounds a star makes before it dies are not just the end of one story, the beginning of countless others. The sound of elements being born, of gravitational waves carrying messages across the cosmos, of the universe itself finding new ways to create beauty and complexity from the ashes of what came before. In the quiet moments after a star has sung its final note, something remarkable happens. The universe doesn't simply move on, forgetting the cosmic symphony that just ended. Instead, it carries those sounds forward, like an echo that travels not through air, but through the very fabric of space and time itself. These gravitational waves, the true sounds of stellar death, ripple outward at the speed of light, carrying with them the story of what just happened in that distant corner of the cosmos. Think of it like dropping a stone into a perfectly still pond. The ripples spread outward in perfect circles, carrying the energy of that impact far beyond where the stone disappeared beneath the surface. But unlike water ripples that eventually fade and disappear, gravitational waves from stellar death can travel for billions of years, crossing vast gulfs of space, carrying their message across the entire universe. When we detect these waves here on Earth, we're not just measuring a scientific phenomenon, we're listening to a story that began long before our planet even existed. The neutron star collision that created the gravitational waves we detected in 2017 happened 30 million years ago, when dinosaurs were just beginning to diversify on our young world. The sound of that cosmic catastrophe travelled all that time to reach us, arriving just as we had finally developed the technology to hear it. It's a humbling thought, isn't it? That the universe has been sending us these messages for billions of years, and we've only just learned how to listen. Each detection is like receiving a letter that was posted eons ago, finally delivered to our cosmic mailbox. And what stories these letters tell! They speak of the most extreme conditions in the universe, of matter compressed to densities we can barely imagine, of energies that dwarf anything we can create on Earth. But perhaps most beautifully, these gravitational waves tell us about connection. They remind us that nothing in the universe happens in isolation. Every stellar death sends out ripples that touch everything else, however faintly. The wave that passes through you as you read these words might have originated from a star that died before our solar system was born. In that sense, you are literally being touched by the echo of ancient stellar music. Scientists have discovered that these gravitational waves carry information that light simply cannot. When we look at a supernova through a telescope, we see the brilliant explosion, but we're seeing only the surface of the event. The gravitational waves, however, carry information from deep within the collapsing star, from regions where no light can escape. They tell us about the core collapse itself, about the exact moment when the star's heart gave up its fight against gravity. It's like being able to hear not just the final note of a song, but also the breath the singer took before hitting that note, the subtle preparation that preceded the climax. Through gravitational waves, we can study the internal mechanics of stellar death in ways that were impossible before. We can measure the mass of the collapsing core, understand the equation of state of matter under extreme conditions, and even probe the physics of strong gravitational fields in ways Einstein could only dream of. The technology that allows us to detect these cosmic sounds is itself a marvel of human ingenuity. The LIGO and Virgo detectors are perhaps the most sensitive instruments ever built, capable of measuring changes in distance smaller than 1/10,000th the width of a proton. To put that in perspective, if the distance from Earth to the nearest star were a human hair, these detectors could measure changes smaller than the width of an atom. When a gravitational wave passes through these detectors, it literally stretches and squeezes space itself. The laser beams that travel down the detector arms get slightly compressed and stretched, and sophisticated computers analyze these tiny changes to reconstruct the original signal. It's an extraordinary feat of engineering that allows us to transform the stretching of space into sound waves we can actually hear. While some stars die in spectacular explosive finales, others leave behind something equally fascinating but far more subtle. These are the pulsars, the lighthouse keepers of the cosmos, spinning neutron stars that sweep beams of radio waves across space like cosmic searchlights. And they too have their own unique songs to sing. Imagine a sphere just 20 kilometers across, but containing more mass than our entire sun. The surface of such an object would be so dense that a sugar cube of its material would weigh as much as a mountain. This is a neutron star, the collapsed core of a massive star that has been compressed to almost unimaginable density. And some of these neutron stars spin, sometimes hundreds of times per second, creating the cosmic lighthouses we call pulsars. When astronomers first discovered pulsars in 1967, the signals were so regular, so precise, that they briefly considered whether they might be receiving messages from an alien civilization. The first pulsar discovered was even given the designation LGM1, standing for Little Green Men. But as more pulsars were found, it became clear that these were natural phenomena, cosmic clocks of extraordinary precision. The sound of a pulsar is created by its rapid rotation. As the neutron star spins, its powerful magnetic field sweeps around with it, accelerating charged particles and creating beams of radio waves that stream out from its magnetic poles. If one of these beams happens to point toward Earth as the star rotates, we detect a pulse of radio energy. It's like a lighthouse whose beam sweeps across us once per rotation, creating a rhythmic pattern that can be incredibly regular. Some pulsars are so stable that they rival atomic clocks in their precision. The pulsar known as PSR J1T13+0747 is so regular that astronomers can predict its pulses years in advance, with an accuracy of better than 100 nanoseconds. These cosmic timepieces are helping us study fundamental physics in ways we never could on Earth. There are natural laboratories where we can test Einstein's theories under conditions of extreme gravity and energy. But pulsars do more than just keep perfect time. They also sing to us about their environment and their history. As a pulsar ages, it gradually slows down, its rotation rate decreasing as it loses energy. By measuring this slowdown, astronomers can determine how old a pulsar is and how much energy it's radiating away. Some pulsars show sudden speed-ups called glitches, moments when their rotation rate suddenly increases, possibly due to starquakes in their incredibly dense crust. The most musical pulsars are those in binary systems, dancing with companion stars in complex gravitational ballets. These binary pulsars provide some of our best tests of Einstein's general relativity. The famous Hulse-Taylor binary pulsar, discovered in 1974, is slowly spiraling inward as it loses energy to gravitational waves, providing the first indirect evidence that these waves actually exist, decades before we could detect them directly. When we convert pulsar signals into audio, each one has its own distinctive voice. Some sound like rapid drum beats, others like cosmic whistles or electronic music. The fastest spinning pulsar known rotates 716 times per second, creating a high-pitched whine that would sound almost musical if we could hear it directly. The slowest pulsars have periods of several seconds, creating a slow, steady rhythm like a cosmic heartbeat. There's something deeply moving about these cosmic lighthouse keepers. They are, in a very real sense, the ghosts of dead stars, continuing to broadcast their presence across the galaxy long after their parent stars have vanished. Some pulsars have been spinning for millions or even billions of years, faithfully sending out their signals to anyone who cares to listen. They are cosmic mementos mori, reminders that even in death, stars continue to shape and influence the universe around them. The study of pulsars has also revealed something unexpected about stellar death. We've discovered that some neutron stars aren't solitary lighthouse keepers, but exist in exotic partnerships. When two neutron stars orbit each other, they create some of the most extreme conditions in the universe. These binary systems slowly lose energy to gravitational waves, causing the two stars to spiral closer and closer together over millions of years. As we step back and look at the bigger picture, something extraordinary emerges. All these different stellar death sounds, the gravitational waves from black hole mergers, the radio pulses from neutron stars, the acoustic oscillations from white dwarfs, they're not isolated events. They're all part of a vast cosmic orchestra, a symphony that has been playing for billions of years across the entire universe. Scientists are beginning to realize that we can use multiple types of these cosmic sounds together to learn things that would be impossible from any single source. This is called multi-messenger astronomy, and it's opening up entirely new ways of studying the universe. When we detect gravitational waves from a neutron star collision, we can also look for the light from the explosion, the gamma rays from the jets, and even the neutrinos that escape from the collision site. Each messenger tells us something different about the same event. The 2017 detection of gravitational waves from colliding neutron stars was accompanied by observations across the entire electromagnetic spectrum. Telescopes around the world and in space turned toward the source, studying the afterglow in gamma rays, X-rays, visible light, infrared, and radio waves. It was like having an entire orchestra playing the same piece, but with each instrument contributing its own unique part to the overall composition. This event, known as GIDO 170811, taught us more about neutron star collisions in a few hours than we had learned in decades of theoretical work. We confirmed that these collisions are the cosmic forges where many of the heaviest elements are created. The gold in your jewellery, the platinum in catalytic converters, the uranium in nuclear power plants. Much of it was likely forged in the incredible heat and pressure of neutron star collisions like this one. But the cosmic orchestra plays on multiple scales of time and space, while individual stellar deaths create brief dramatic crescendos in this symphony. There are also longer, more subtle movements that unfold over millions and billions of years. The collective effect of all stellar deaths in a galaxy shapes its structure and evolution. Supernova explosions blow bubbles in the interstellar medium, creating cavities hundreds of light years across. These supernova remnants heat and stir the gas between stars, influencing where and how new stars will form. On an even grander scale, the heavy elements forged in stellar cores and scattered by stellar explosions gradually enrich the galaxy with the raw materials needed for rocky planets and life itself. Every atom in your body heavier than hydrogen and helium was forged in the core of a star, or in the explosive death of a star. You are literally made of stardust, assembled from the ashes of stars that died billions of years ago. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created by nuclear fusion in stellar cores or in the incredible energies of stellar explosions. In a very real sense, you are the universe's way of understanding itself, assembled from stellar remnants and animated by the same fundamental forces that power the stars. This cosmic recycling has been going on for most of the universe's history. The first stars contained only hydrogen and helium, the primordial elements created in the Big Bang. But when these first massive stars died, they seeded space with heavier elements. The next generation of stars incorporated these elements, lived their lives, and added even more heavy elements to the cosmic inventory. Each successive generation of stars is built upon the legacy of those that came before, gradually enriching the universe with the complex chemistry needed for planets, weather, oceans, and life. From this perspective, stellar death isn't really an ending at all. It's a transformation, a passing of the torch from one generation of stars to the next. The sounds of dying stars are really birth songs, announcing the creation of new elements and new possibilities. Every supernova is both a funeral and a baby shower, marking the end of one star's life while celebrating the potential for countless new worlds. As we have learnt to hear the sounds of stellar death, we've also begun to imagine what we might hear in the future. The current generation of gravitational wave detectors is just the beginning. plans are already underway for far more sensitive instruments that will be able to detect stellar deaths from much greater distances and with much greater precision. The European Space Agency is planning a space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna. Unlike ground-based detectors that are limited by seismic noise and other terrestrial disturbances, LISA will consist of 3 spacecraft flying in formation, separated by millions of kilometers. This cosmic-scale detector will be sensitive to gravitational waves with much lower frequencies than we can detect on Earth, opening up entirely new types of cosmic sounds. LISA will be able to hear the gravitational waves from massive black holes as they spiral into each other over periods of months or years. It will detect the enspiraling of white dwarf stars in our own galaxy, creating a kind of cosmic background hum made up of thousands of these binary systems. It will even be sensitive enough to detect the gravitational waves from the phase transitions that occurred in the first fraction of a second after the Big Bang, if such waves exist. On an even larger scale, astronomers are using arrays of pulsars as gravitational wave detectors. These pulsar timing arrays monitor dozens of millisecond pulsars across the galaxy, looking for tiny changes in their pulse arrival times that would indicate the passage of gravitational waves. These arrays are sensitive to waves with periods of years or decades, complementing the seconds to minutes sensitivity of detectors like LIGO. The sounds we'll be able to hear with future detectors will tell us stories we can barely imagine today. We'll be able to study black holes with masses millions or billions of times that of our Sun as they merge with each other. We'll hear the gravitational waves from the first stars that formed in the universe, if any of them were massive enough to create detectable signals. We might even detect sounds from exotic objects that we haven't yet discovered or understood. But perhaps the most exciting prospect is that we'll develop a much richer understanding of the cosmic orchestra itself. As our ability to detect gravitational waves improves, we'll begin to hear not just individual events, but the collective sound of stellar deaths across the entire observable universe. We'll be able to map out the history of star formation and stellar death across cosmic time, listening to the universe's own musical autobiography. There's also the tantalizing possibility that gravitational waves might carry information about physics beyond our current understanding. Just as visible light taught us about the electromagnetic force and atomic structure, gravitational waves might reveal new aspects of gravity, space, and time that we haven't yet discovered. The sounds of stellar death might contain encrypted messages about the deepest workings of reality itself. Some scientists speculate that we might even be able to detect gravitational waves from the quantum fluctuations of the vacuum itself, or from the cosmic strings that some theories predict were created in the early universe. These would be the faintest whispers in our cosmic symphony, requiring detectors far more sensitive than anything we can build today. But if we could hear them, they would tell us about the universe's birth itself. As we develop these new ways of listening to the cosmos, we're also learning to interpret the sounds we're already hearing. The field of gravitational wave astronomy is still in its infancy, and each new detection brings surprises. We've already discovered that black hole mergers are more common than we expected, that neutron stars can be more massive than we thought possible, and that the universe is filled with a symphony of sounds we're only just beginning to appreciate. As our journey through the sounds of stellar death draws to a close, it's worth reflecting on what we've discovered together. We began by wondering about the sounds that stars make as they die, and we've learned that stars don't just make sounds. They are sounds in the deepest sense. Every star is a vibrating, oscillating, resonating structure, singing its own unique song throughout its lifetime and composing a final movement as it approaches death. We've discovered that the universe is far from silent. It's filled with music, the acoustic waves that travel through stellar interiors, the gravitational waves that ripple through space-time itself, the radio pulses from spinning neutron stars, and the collective harmony of billions of stars all playing their parts in a cosmic symphony that has been performing for nearly 14 billion years. But perhaps the most beautiful discovery is that this cosmic music doesn't just exist in some abstract theoretical sense. It's intimately connected to our own existence. The sounds of stellar death are the sounds of creation itself. Every heavy element in your body was forged in a stellar core and distributed by stellar death. The energy that powers your thoughts comes ultimately from nuclear fusion, the same process that makes stars shine and sing. You're not separate from this cosmic symphony, you're part of it, a living, breathing note in the universe's endless song. When you look up at the night sky, remember that you're not just seeing distant points of light. You're seeing fellow musicians in the cosmic orchestra, each one singing its own song, each one contributing to the grand composition that fills the universe. Some of those stars are in their vigorous middle age, singing strong, steady songs like our own sun. Others are ancient giants, approaching their final movements with increasingly dramatic crescendos. Still others have already fallen silent, leaving behind only their echoes in the form of white dwarfs, neutron stars or black holes. The gravitational waves from stellar deaths that pass through us every day are like cosmic sheet music carrying the mathematical harmonies of Einstein's field equations across billions of light years. When these waves reach our detectors, we're not just measuring a physical phenomenon, we're reading the universe's own musical notation, translating the mathematics of curved space-time into sounds we can understand and appreciate. In a sense, we are the universe's way of listening to itself. Through us, the cosmos has developed ears capable of hearing its own music. The atoms that make up our brains and our instruments were forged in stellar cores, and now those same atoms have organized themselves in such a way that they can detect and appreciate the sounds of their own cosmic origins. It's a kind of poetic justice that matter created by stellar death should eventually evolve the ability to hear the sounds of stellar death. The study of stellar sounds has also taught us about the nature of time itself. When we detect gravitational waves from a stellar collision that happened a billion years ago, we're not just receiving information about that event, we're actually experiencing it. The waves that stretch and compress our detectors are the same waves that were created by the collision itself. In a very real sense, the past is still happening, still rippling through space, still available for us to experience directly. This gives us a unique perspective on our place in cosmic history. We exist at a special moment, just as our species has developed the technology to hear the universe's deepest songs. For most of human history, we could only see the universe, experiencing it through light and electromagnetic radiation. Now, for the first time, we can hear it as well, experiencing space-time itself as it vibrates with the echoes of cosmic catastrophes. The sounds of stellar death remind us that endings and beginnings are often the same thing, viewed from different perspectives. A supernova represents the death of one star, but it also represents the birth of a neutron star or black hole, the creation of heavy elements, the seeding of space with the raw materials for new worlds, and the injection of energy that will trigger the formation of new stars. Death and birth, ending and beginning, silence and song. In the cosmic symphony, these apparent opposites are revealed to be different movements in the same composition. As we continue to develop more sensitive detectors and more sophisticated analysis techniques, we'll undoubtedly discover new types of cosmic sounds that we can't even imagine today. The universe is full of exotic objects and extreme phenomena, many of which probably generate their own unique acoustic signatures. We're like musicians who have just learned to hear the string section of a vast orchestra, gradually becoming aware that there are also brass instruments, woodwinds, percussion, and perhaps instruments we don't even have names for yet. The sounds of stellar death also remind us of our responsibility as cosmic listeners. We are the only species we know of that can detect and appreciate these cosmic symphonies. With that ability comes a kind of obligation to listen carefully, to preserve and share what we hear, and to continue developing our capacity to hear even more. We are the universe's only known music critics, and the reviews we write, in the form of scientific papers, educational materials, and cultural works inspired by cosmic discoveries, help ensure that the universe's music will be appreciated by future generations. In the end, the sounds that stars make before they die are not sounds of finality, but sounds of transformation. They are the universe's way of composing itself, constantly writing new melodies from the themes established in earlier movements. Every stellar death adds new harmonies to the cosmic composition, ensuring that the symphony grows richer and more complex with time. As you go about your daily life, remember that you are surrounded by this cosmic music. Gravitational waves from distant stellar deaths are passing through you right now, stretching and compressing your body by amounts far too small to feel, but large enough to measure with our most sensitive instruments. Radio waves from pulsars are streaming past you, carrying the rhythmic messages of cosmic lighthouses. The very atoms in your body are humming with the quantum vibrations that give matter its structure and properties. You're not just listening to the cosmic symphony, you're part of it, contributing your own small but irreplaceable note to the universe's endless song. And someday, billions of years from now, when our own sun begins to sing its final song, the sounds it makes will carry forward the music of our solar system, our planet, and our species, adding our own melody to the eternal composition that fills the cosmos. The universe is singing, and it always has been. We've simply learned how to listen, and in learning to hear the sounds that stars make before they die, we've discovered that death itself is not an ending, but a modulation into a new key, a transition to a new movement in the endless symphony of existence. Thank you for staying with me through this peaceful journey into the sounds that stars make before they die. I hope that next time you look up at the night sky, you'll remember that you're not just seeing a collection of distant lights, but witnessing a cosmic orchestra in the middle of its performance. The stars are singing, space itself is ringing with the music of gravity, and you, made of stellar ashes and animated by nuclear fire, are both audience and performer in this grandest of all symphonies. Take care, keep listening to the cosmos, and remember that every sunset is accompanied by a stellar song, every dawn by the whisper of gravitational waves, and every moment by the gentle rhythm of a universe that has been composing its masterpiece for nearly 14 billion years. Sweet dreams. And may your own dreams be filled with the peaceful sounds of the cosmic symphony that surrounds us all.